potential energy, we used the force. The force concept was equal to, the force was equal to m times g. Notice that m times g was constant throughout the entire fall of the mass. Okay. Did you ask yourself, well, what happens if suppose the mass was way up in the atmosphere that is way up in space, and it falls down to Earth? There, certainly the effect of gravity is not constant, and that's true. We could certainly have derived that equation with the idea that the gravity changes as it falls. We could certainly do that. That's a harder concept to do. We would have to invoke the law of gravitation in order to do that, but it's very doable, and in more advanced physics books, that's exactly what they do. But here, let's introduce the idea that, let's look at, suppose we have this idea. Suppose the force is equal to mass times acceleration. We're just going to use Newton's second law, but we're going to use the concept that the force is constant. Okay, the force is constant. So what would this, what is an example of this? An example of this would be, suppose suppose you have probably an easy way to comprehend this would be, suppose you have a rocket, and the rocket has a jet engine here, and this jet engine, this is the rocket, and the jet engine here supplies a thrust, a force backwards, and the rocket is propelled forward. Okay? That's Newton's third law. There's thrust going backward, and the rocket is propelled forward. That's Newton's third law. So, because of the thrust going backwards, there's a propelling force forward on the rocket. Is a force that projects the rocket forward. And let's assume, well, the force is equal to its mass times acceleration. And let's make the big assumption right now that the force is constant. Now, actually, we know from rocket theory, if you studied rocket theory a little bit, when a rocket fires, the mass actually is thrust out. Okay, and so it's losing mass as the rocket thrusts forward. But for right now, to make it easy, to make it easy to understand, we're going to assume that the mass stays constant and the force is constant. Okay, let's say we're in outer space, so there's no other forces on this. Essentially, no other gravitational forces. We're free of gravitational forces, let's assume. Remember, this is an idealized experiment. It has a certain velocity, initial velocity. We put in a constant force. This is a constant for a certain amount of time. And what's going to happen? The rocket's going to accelerate from an initial velocity to a final velocity. Okay, so during this period of time, there's a constant force. Okay? Now, this looks very similar to one of the problems, like a problem we would have looked at back in, what was it, chapter 5 maybe, where we started to introduce this idea. Okay, or 4 even, where the acceleration, and there's a certain length of time here, from here to here. Okay, the acceleration is a change of velocity over the change of time. Right? So the change of velocity here is the final velocity minus the initial velocity divided by the time. Again, assuming we have a constant force, this is a constant force leading to a constant acceleration. C means constant in this case. Okay. So far, so good? Okay. Now, let's look at this. If this force is constant, okay, from here to here, what distance has been traveled? We're going to call this distance x. From here to here, and this x is also, well, we'll call it delta x, and it takes a delta t time to traverse from here to here under constant force. Let's calculate the distance, okay, that this has traveled. Okay, how do we do this? Well, we know one simple way to do it is this. Think of the equations back to chapter 2 and the equations back in chapter 4. This distance traveled is equal to the average velocity, I'll call average velocity, times delta time. Now the velocity is not constant. The velocity is changing, but there's the average velocity. Because the velocity is changing continually and smoothly, right in the middle we have an average velocity. We can calculate an average velocity, and that average velocity is simply the initial velocity plus the final velocity divided by 2. That's the average velocity. And so we can say that the distance traveled, the displacement, it's really a vector, is the average velocity, the initial plus the final divided by 2 times delta t. Okay, so what we have here is we have the acceleration and we have the time. Now let's go back up here to our work concept. The amount of work, now what we're going to do is we're going to figure out the amount of work done between these 2 points, point 1 to point 2. In other words, how much work was put into the rocket from here to here. We may say it the change of work. How much, we can also say, another way to think about it is how much energy did it take to move the rocket from here to here to accelerate the rocket from this velocity to this velocity. It took a certain amount of energy, and that's what we're going to calculate here. So one way to think of this is the energy needed to accelerate the rocket from this velocity to a faster velocity. It takes energy to do that. The energy is equal to the force necessary to accelerate it times the displacement. Okay? The force is m times a, mass times acceleration, that's Newton's law, times delta x. Okay? We just calculated what the acceleration is. The acceleration is a change in velocity divided by time, so we're going to substitute. The acceleration is that's the acceleration. Now the change in the displacement is given by, we just evaluated the displacement, is the average velocity times the time. So over 2 divided by delta t. Okay. So at this point, unfortunately, I'm going to have to erase this down here, but you understand what we did? The energy needed to accelerate the rocket from an initial velocity to a final velocity is the force, the energy needed, or the work done on the rocket, is the force times the displacement. The force is simply given by mass times acceleration. We're going to assume this is a constant acceleration. We define our acceleration the way we normally do, just right back in chapter 2, change of velocity over change of time, and then we put in the displacement. We calculate the distance traveled, the displacement, simply the average velocity times the time. We substitute that in, and now we have to evaluate this. So I'm going to erase this. Okay. And notice at this point we haven't even used any calculus. At this point we don't need to use calculus because we're talking about forces that are constant. Okay, so we're going to evaluate this. We have mass. Well, notice first of all that the delta t's cancel out. That's very nice. So the time actually drops out. What we're left with is m over 2 m over 2 times, we have Vf minus Vo times Vo plus Vf. Okay? Now, to make things a little bit easier, I'm just simply going to reverse the order of these, and I'm going to say Vf plus Vo. I can do that. I can simply reverse the order of these. Okay, makes it a little bit easier, at least for me, to multiply. Okay, I'm going to put 1/2 m times, and all of this is in parentheses. I'm going to evaluate this, and you remember from algebra how to multiply this. Vf, I have Vf squared. Vf squared. My inner product and my outer product, I have a minus Vo Vf, V sub f, and the outer product here is plus Vo Vf, and then minus Vo squared. Notice these cancel out. These add up to 0, and what I'm left with is 1/2 m times the final velocity squared minus the initial velocity squared. Okay, well, let's separate those. And I have 1/2 m, the final velocity squared, minus 1/2 m, the initial velocity squared. I'll put those in parentheses. Okay, so this is the work, the work needed, or let me say this, it's the energy. I'm going to write, in this case, I'm going to write it as E, the energy, the required energy. Required energy, energy. Okay, so notice we have what we have derived here is that the energy needed is 1/2 m, the final velocity squared, minus 1/2 m, the initial velocity squared. We have a difference here. Okay, what is kinetic energy? 1/2 mv squared. So apparently what we have derived is that you all have this. I'm going to erase this right now and put it right up here, that the energy needed equals 1/2 m, the final velocity squared, minus 1/2 m, the initial velocity squared. Okay. Now we're going to interpret what all this means. Okay. Our interpretation goes like this. When the rocket had an initial velocity, okay, we applied a force to it. The rocket had initial velocity Vo. At this point here, it has a final velocity Vf. It's larger. Between here and here, we applied a force to it. A force to it, which was mass times acceleration, and that was a constant force. Okay, we applied a constant force, and that took energy. So energy was put into the rocket. That means that some amount of energy, some had to push the rocket, and that took energy. And that amount of energy is given by the right here. So the one way we can interpret that is that the final energy, if we say that the change of energy of the rocket is the final energy minus the initial energy. This is the final energy. The final energy of the rocket is given by 1/2 m v squared. The initial energy over the rocket over here is equal to 1/2 m v initial squared. Notice the formula is the same. 1/2 mv squared initially, the initial energy is 1/2 mv squared, where v is the initial velocity. The final velocity, the final energy, is given by 1/2 mv squared, where v is the final velocity, and the difference here is delta E. The energy you put into it is the difference between the final energy and the initial energy. So all this makes sense from a physics point of view. The rocket has an initial energy, we give it a boost of energy, and it has a final energy that's higher. Okay, and now there is a way to derive this also, assuming that the velocity is not constant. That the force is not constant. Let me see how much time we have here. Do I have time to do this? Tell you what, I'll do this real quickly. This may be rather fast, but you understand I understand, I hope, how we have derived this 1/2 mv squared as being the kinetic energy. What I'm now going to do, just real quickly, and if I lose some of you, I'm sorry, but just for completeness sake, it might be fun to do this, is to derive the same equation, but with the idea that the force actually is not constant. Okay, let's look at the same thing, that the change of work equals a force times the change of distance. But let's assume that F is, again, F is not constant. Okay. Okay, in this case, if the force is, now the F is still mass times acceleration. If the force is not constant, what does that mean? That means that the acceleration is not constant. If the acceleration is not constant, the acceleration changes. That means we cannot use the concept of average velocity. The velocities are changing all over the place, potentially, and it's not in any kind of average way that we can calculate an average velocity, at least not so easily. So how do we handle that concept? Well, we invoke, again, this is going to be, just real quickly, this is going to invoke some calculus here. Acceleration, let's look at the definition of acceleration. It is the change of velocity over the change of time. Now, in the limit, I'm going to say as the limit, in the limit is the calculus, as delta t approaches 0, this changes to the differential velocity over the differential, well, excuse me, I wrote it the wrong way. In the limit, as delta t approaches 0, this ratio approaches the derivative of the differential v divided by the differential t, and it's called the derivative of the velocity. That's what we mean by the derivative. Okay? Now, what we're going to do is we're going to invoke what we call the chain rule. The chain rule goes like this. I'm going to do it, look at it easy way. I'm going to introduce another variable, delta x. Notice the delta x's cancel out, so you may say, well, why do that? It's still delta v over delta t, but it allows me something. I'll show you why. Okay, so basically what I have is I have as delta t approaches 0, I have the derivative. So I have the derivative of v with respect to x times derivative of x with respect to t. Now, what is dx dt? That's the same thing as velocity. X over t is the same thing as velocity. Okay? So, come over here to this work concept. I'm going to put the work in, the force, at this point, the force, which is mass times acceleration, I'm going to substitute this. Acceleration is now v, I'm going to switch the order of these, times dv dx. Okay. Now, it's not clear what that's going to give me here, but this is still a valid equation. I'm going to substitute this into here, and I have that the differential work, the small amount of work, is mass times velocity times dv dx, and this becomes dx. Okay, this is mass times acceleration, and this is the delta x. In the limit, it becomes dx, differential x. Notice now that the x's cancel out, the little differential s's cancel out, and I have that the differential amount of work is equal to the mass times velocity times differential velocity. Okay, at this point, now this is, even if you don't follow this from a calculus point of view, it would be good, you can still follow this, I think, that the total work done, I integrate all the little dw's, same thing as summation, I sum over all the little dw's, okay, from a velocity. In this case, I'm integrating with respect to v, dv, so I say a velocity from an initial velocity to a final velocity, initial velocity to a final velocity. And I get m, integrate m, v, dv from an initial velocity to a final velocity. Okay? And the mass is constant, so we can pull that out, and we get v dv from initial velocity to the final velocity. Now, if you know calculus, how do we integrate this integral? For those of you who are doing calculus, we know it would be 1/2 v squared evaluated, and if you don't know calculus, it looks like I just pulled that out of the air, but this is a calculus, basically a calculus integral. You'll learn this eventually. Evaluated from the initial velocity to the final velocity. So, to evaluate those limits, I go 1/2 m, the final velocity squared, minus the initial velocity squared. So, what I have here is the exact same thing. That, let's see, can you all read this down here? I'm going to put this right here. That the work done is a 1/2 m, the final velocity squared, minus 1/2 m, the initial velocity squared. This is the exact same thing we just calculated actually before. But in this case, we calculated based on the idea that the force is not constant, the acceleration is not constant, but we still get the exact same formula, okay, which is very good to know. So in other words, this idea of kinetic energy being 1/2 mv squared is valid whether or not we have a constant acceleration or not a constant acceleration, whether we have a constant force or not a constant force. This is still a valid energy, this is still the right way to evaluate the energy of something in motion. Okay. At this point, what we want to do is to just continue on through the chapter. We've really introduced a lot of, we spent a lot of time very early on in the chapter on page 255. We're still on page 255. And what we just went over is really not in the book. But I thought it important to actually go over that so you can see how this is actually derived. And hopefully it gave you some good concepts to understand how this actually works. If we go to page 260 and 261, let's look at, I'm going to make up some example problems. This is on page 258. Suppose we have a mass well, suppose we have a car. Suppose it's a toy car, and you push it like this, and it goes. Okay, so it's a toy car on a track, and you push it like this, and this distance from here to here is h1. This distance from here to here is h2. Okay, how does the energy concept work? The energy concept is this, that the total energy of the car, we see total energy equals T, we'll just give it the abbreviation TE, is equal to the potential energy plus the kinetic energy. Okay? So at any given time, the total energy of the car is the same. Now again, we're making the assumption that the car does not have a rocket. Assuming we don't have a rocket on this car, that there's no energy that you're putting into the system, that is from outside. So if this is a conservative system, meaning you're not putting energy into the car, like from a rocket engine or a motor or something like that, that the total energy at this point, number A, is the same as the total energy at this point B, and the same as the total energy at this point C. Okay, so we might say that the total energy in position A is equal to the total energy at position B, and that's also equal to the total energy at position C. Okay, but notice that in each of these positions, the total energy is broken between two components. So let's say at this point right here, the total energy at position A is all potential. Let's say there's no kinetic energy at this point. Let's say this is just about ready to slope down. So it can move, but not quite. We're holding it back. So the total energy here is, and we're going to use our datum right here of us. This is our datum where we're referencing all of our potential energy to. Relative to this point right here, this point elevation, the potential energy is a mass. This car has a mass of m times g times h1. Okay, that's the total energy of the car with reference to this reference point right here. We'll call this the datum or the reference point. Reference point. Okay, now that equals the total energy at B, right here. Here's point B. So the total energy here, again, total energy at B is mg, well, h in this case is 0. So actually, there is no potential energy. The h is 0. Right here, h is 0. So therefore, the mgh component drops out, and it's all, I'll say, potential energy at B is equal to 1/2 m v of B squared. Okay? So all the energy is locked into kinetic energy, is transferred into kinetic energy. So basically, at this point, we have all potential energy. It rolls downhill. All that potential energy is transferred into kinetic energy, 1/2 mvb squared. So we could very easily calculate what the velocity was at point B. The velocity at point B, this is mg h1. The velocity, notice that the masses cancel out, and we multiply the 2 over here, so we get 2g h1, and then we have to take the square root. Okay? So we can very easily calculate the energy right here of the car at the B position just from a pure, we can calculate the velocity right here just from the energy concept, that the potential energy is converted to kinetic energy. Okay? So that would be the velocity at point B. Now suppose we wanted to calculate this, so the car comes down here, but then there's a lot of momentum and the car comes up here to point C. How do we calculate the velocity at point C? Okay. We know that the total energy of A equals the total energy of B, and that's also equal to the total energy of C. Now the total energy of C will be a combination of potential and kinetic. It will be the potential energy at C plus the kinetic energy of C, and that's the potential energy of C is mgh2, this distance from here to here, plus the kinetic energy, mg velocity of C squared. We don't know what that velocity is, but we're just going to give it a velocity name vc, and we know that it's 1/2 mv squared. Okay, so the kinetic, so let's calculate, how would we calculate the velocity, this velocity here?